We ourselves cannot venture into deep space, but we have sent explorers, mechanical explorers, to distant planets and to the outer reaches of our solar system, to be our eyes and our ears. These spacecraft, however, are only as good as our ability to communicate with them, to track them and to guide them, and above all, to receive the data they send back. Antenna stations in the United States, Spain, and Australia form a network around the Earth. They maintain 24-hour communication with spacecraft flying throughout the solar system. This global communications network makes possible the transformation of radio signals into scientific data. This deep space network is operated for the National Aeronautics and Space Administration, NASA, by the Jet Propulsion Laboratory in Pasadena, California.
Okay, we are standing here looking over the hub of the Deep Space Network, where the three complexes, Goldstone, Madrid, and Canberra, are controlled from this room. The operations chief and his team of network controllers are communicating with both the flight projects in other rooms in this building, as well as the stations around the world, to direct the operation of those stations in support of the spacecraft.
The Deep Space Network was created to answer a need.
The Deep Space Network worldwide facilities were basically established because the early spacecraft did not have recording media or storage mechanisms for storing the scientific data. So anytime there wasn't a tracking station looking at it, that scientific data was lost. The missions that the DSN has been involved with started with the Ranger series of missions that went to the moon, the Mariner missions, which went to Venus and Mars, followed by Surveyor, which landed on the moon, Lunar Orbiter that photographed the moon extensively for Apollo, Pioneer 6 through 9, which were interplanetary missions circling the sun, between the Earth and the sun, Pioneers 10, 11, which are now out towards the edge of the solar system, that were the first missions to go to Jupiter. Pioneer 11 went to Saturn also. It was a precursor for Voyager. Pioneer 12, which was returned to Venus and dropped 5 probes on Venus. And of course in Voyager, which we're still supporting, and made vast changes in the network to support Voyager as it's gone out to Uranus and Neptune.
The 3 Deep Space Network stations are spread out at strategic locations 120 degrees apart in longitude. This allows for continuous communication with spacecraft as the Earth rotates. In Australia, the complex is located at the Tidbinbilla Nature Reserve near the capital city of Canberra. It is staffed and operated by the Australian Department of Science.
The biggest role, of course, for a tracking complex such as Tidbinbilla or any others in the DSN, Deep Space Network, is to be able to communicate with spacecraft, typically commands up and receiving data down. That, however, is only half of the total task that needs to be done. That data needs to be presented or moved or somehow or other placed in front of the experimenter, the person who knows what a particular part of the spacecraft is doing and what it should be doing. Therefore, a vital part of the network is what one can call ground communications or terrestrial communications. That is, how to get the data necessary between a complex such as this and the Spacecraft Operations Center.
The Spanish complex at Robledo is near Madrid. The complex is operated by the Spanish National Institute of Technology and Aerospace.
As you can see, we've been increasing the sizes of the antennas because obviously the exploration of the space as we were going to farther out in the space, going to the planets, the outer planets, then we need more aperture, more antennas, just to get enough capacity to receive the signals from the outer space. With this antenna, the 70-meter antenna and the original 61, we can array the 3 antennas to get the maximum signal for the encounters of Voyager, especially in Uranus and Neptune.
In California, the Goldstone complex is operated by JPL and contractor employees. It is located in the Mojave Desert near the city of Barstow.
The exciting part of this program is the fact that we are able to communicate with spacecraft that are so far away, and the signals are so minute, and we're able to direct the spacecraft to take pictures of a planet as it flies by, to measure temperatures, to measure solar winds. It's just, if you really sit down and you think about the amazing part of this thing, that we're talking to spacecraft that are billions of miles away, and we are going to continue to do this for the next 20 years with these same spacecraft.
The basic functions performed by NASA's relay satellites and the Deep Space Network are to receive the downlink signals from spacecraft, to send commands to spacecraft, and to track spacecraft as they travel throughout the solar system. The instructions to spacecraft are formatted into what are called command loads. These digital commands are sent through microwave or satellite links to one of the 3 deep space stations.
The DSN has antennas that are focused on the spacecraft. The spacecraft has an antenna that's focused on the DSN. And as long as these 2 antennas are looking at each other, you can use a lower power to communicate. But if the spacecraft ever drifts off the DSN point, and where you have to communicate with an omni antenna, which is a low gain antenna requiring more power, we then require something on the order of 400 kilowatts to be able to transmit to the spacecraft. And this is really important because otherwise you may lose the spacecraft. If you have some problem that caused the spacecraft to drift off and you have to command it to repoint the antenna.
All of the commanding, what we refer to as commanding, is generated at the NOCC, which is the Network Operations Control Center located in JPL, Pasadena. The signals are sent from the NOCC to the spacecraft, asking the spacecraft or telling the spacecraft to perform a certain function.
Ready to copy. I am ready to copy.
The result of that is transferred back from the spacecraft to the antenna here on the ground. The antenna collects the data. The data that is collected by the antenna is then passed on to a receiver system. From that point, the information out of the receiver system is transferred to a telemetry system, or to a tracking system, or to both. There it is data formatted and transferred from here to the NOCC, which then is distributed to the user.
Information returned to Earth through the Deep Space Network has revolutionized our knowledge of the solar system. Images from space have changed the way we think of other worlds. In the 60s and 70s, the Deep Space Network played a crucial role in NASA's venture to place men on the moon. In 1976, it was the Deep Space Network that received the first communications from the surface of Mars.
The first Viking lander, of course, was a kind of a, I don't know how to say it. It was a breathtaking event. We didn't have communications with the lander itself through the complete landing, and we finally did get communications, which came back through the Viking orbiter that indicated it had landed successfully. Of course, it was a big relief to a lot of people, and one of the things that the network was concerned about is maintaining that communication link through that whole time, because otherwise it would not have been able to verify that the spacecraft had successfully landed. And it was just a very enjoyable time when that thing finally set down and wasn't destroyed.
The network was also there to track the re-entry of the first space shuttle, Columbia. Goldstone provides tracking support for all the shuttle landings at Edwards Air Force Base in California. Since its inception, the Deep Space Network has been a one-of-a-kind resource, unique in all the world. The space agencies of Europe, Japan, and the Soviet Union have all used the network to guide many of their spacecraft in exploring the solar system.
The operation of the Deep Space Network has really from the outset been an international affair, and 2 of our 3 complexes are operated by other countries, Spain and Australia. And recently we have been seeing increasingly that NASA's major new missions all include international participation. What this means to the network, I think, is that in the future we can increasingly expect to track other countries' spacecraft, and in return to have our capabilities augmented by other countries' tracking capabilities. We have seen that already, for example, with the Soviet missions to Venus, the Vega mission, and the Phobos mission. In addition, there was really an international armada for the Halley Comet encounter, which was covered by the DSN. The Voyager encounters have relied on both the capabilities of the Deep Space Network and radio telescopes from around the world. Now, this will pose some special requirements and I think affect the way in which the DSN develops because there is the issue of interoperability. That means that we need to be able to operate at the same frequency that our international partners are operating, and we need to adopt the same kinds of standards for data handling that other countries use. And we would like to take the lead in ensuring that our capabilities are compatible with theirs.
In the case of the Voyager missions, the 70-meter antenna alone is insufficient. We developed a capability a number of years ago to array antennas together, to where you essentially receive the data simultaneously on different antennas. You electrically connect those antennas together and sum up the energy to detect the signal.
The arraying technique was first carried out at the Australian tracking site.
But there comes a point beyond which an antenna cannot be practically made much bigger, and therefore in the case of the Australian continent, when it came to Voyager's flyby of Uranus, we had to look around, or NASA had to look around in conjunction with ourselves in Australia and see what could be done about it. There is 200 miles north of this complex at Tidbinbilla a 64-meter, 210-foot antenna known as the Parkes radio telescope. This antenna has a capability more or less equivalent to the DSN antennas. It's a slightly different design, but what we ended up doing was installing equipment at the Parkes radio telescope and putting in a microwave link, all of 200 miles, a dedicated microwave link, which allows us to receive the signal at Parkes, bring it down here to Tidbinbilla, and then using electronic combining techniques to be able to turn out the signal as if it was one giant antenna. Effectively, it does the job of one antenna twice as big.
The same technique is used with the very large array in New Mexico. 27 antennas are electronically linked with the Goldstone complex in support of planetary missions. While the work of the Deep Space Network has become more complex, computer support has simplified operations at each facility. The ongoing task of maintaining this global network, however, cannot be automated. Hundreds of technicians and computer specialists work to ensure that each piece of equipment operates in peak condition around the clock. Besides being a communication system, the Deep Space Network is also used as a scientific instrument to observe the universe.
Antennas became important instruments for radio astronomy. It's now about 20 years ago, and it happened because we needed a large antenna for communication between the Earth and spacecraft going out to the outer planets and to the edge of the solar system. As soon as it became operational, radio astronomers began to solicit time to do their experiments.
Radio astronomy techniques provide a totally different view of the sky than that seen through other types of telescopes. Used as radio telescopes, the Deep Space Network antennas probe stars, galaxies, quasars, and vast molecular structures in the universe. Spacecraft radio transmitters are also used to make important measurements.
When a radio wave passes through atmospheric elements, those atmospheric elements will perturb the radio wave, and they will perturb it in such a way that's measurable. And you can then, once you can measure this, you can relate it to some characteristic of that atmosphere. So one of the experiments we do is, as the spacecraft flies through planetary atmosphere, we have some very stable and sophisticated equipment on the ground that measures the perturbation to that radio signal, which is then analyzed to characterize the atmosphere of the planet.
Perhaps the most intriguing effort undertaken by the network is the search for extraterrestrial intelligence, called SETI. The SETI program, conducted by JPL and the Ames Research Center, will operate from the Goldstone Complex. Here, astronomers will sort through the billions of radio signals from natural sources in search of a transmission from intelligent beings. JPL researchers are devising ways to improve the sensitivity and power of the Deep Space Network.
In the near term, at least, I'm not expecting that the basic configuration of the DSN will change much. I think the 70-meter antenna size is about as large as is really practical to go with a fully steerable antenna. We will have to look to other techniques to improve the capabilities of the network, including going to higher frequency bands, arraying antennas, more sensitive receivers, and other techniques of that sort. As we move out in time into the more distant future, and we look forward to the use of optical communication, for example, then you can contemplate basically different configurations for the DSN, including doing some things in orbit that we're currently doing on the ground, but I see that as being well into the next century. A very major development will be the manned exploration of the solar system, with all of the requirements that go along with having a very reliable, highly capable network for that purpose. I believe that the DSN will play a role, an important role in that. Certainly the techniques that have been developed within the network are going to be used in those missions, and will really stretch our capabilities in terms of the requirements for those missions.
The Deep Space Network has guided spacecraft to 8 of the 9 planets in the solar system. future generations, as spacecraft from Earth venture outward into the universe, the Deep Space Network will continue to be our eyes and our ears.
We added filler to the line to give you a